Hello, good morning or good afternoon for those of you listening from the Far East, and welcome to the GeoTeric webinar of this month, which is going to be about how to validate your frequency decomposition color blends using our new GeoTeric Validates Wedge Model module. So just to start, I will show you a few slides and then we will go into a live demo showing you Validate in action. So Validate is a new module of GeoTeric, which requires a separate license. It was released for the first time a few months ago in GeoTeric 2018.1, and that first release included the layer model, and then later on we added the wedge model, which is available from GeoTeric 2018.1.2. So today we are going to focus on the wedge model, and the idea behind Validate is to have a tool that will allow us to validate and to get more confidence on the colors that we see in our RGB color blends. So when we use the wedge model, the main objective is to test different thicknesses and how different thicknesses of our different layers will have a different color response in an RGB frequency decomposition results. So today we are going to be looking at a small case study here from the northwest of Australia. We have a 3D seismic available for the area, the HCA 2000 dataset, which is provided by Geoscience Australia. And there are two wells drilled on this area. There is the Eskdale 1 and Eskdale 2 wells, as you see there. So what we have here is the top reservoir horizon with a frequency decomposition color blend mapped onto it. And as I said, the idea of Validate is to be able to understand a little bit better our colors and what kind of geological features or responses are behind each of these colors that we see. And in particular with the wedge model, what we try to test is different thicknesses and how thickness variations might be impacting those colors that we see. So as I mentioned, there are two wells on this prospect or in this field. So Eskdale 1 was the discovery well, and it found 75 meters of sand. You can see here the gamma ray log. So yeah, between the top reservoir and base reservoir is about 75 meters. Then a second appraisal well was drilled, Eskdale 2, and that one only found 37 meters of sand. So I think with this study, what we are going to do is we will start with Eskdale 1, and we will model. We'll create a model based on the results from Eskdale 1, and then we will try to predict what thickness is expected in the area where Eskdale 2 was drilled. So I'm just going to start now in GeoTeric, and we are going to show you a live demo of this field. Yeah, so I've got GeoTeric up here. Now you can see here the top reservoir horizon shifted down 20 milliseconds so that we go through the reservoir interval. And you can see this is the discovery well here giving us some kind of blue to green response. And then we've got the appraisal well, Eskdale 2, giving us here some sort of reddish to yellowish. You can see it's just in the edge of the red to the yellow response. So now if we want to start to understand why we got different thicknesses in the wells and why different colors might represent different thicknesses, we can use Validate. So you will see in GeoTeric, we've got now a new module here in our toolbar called Validate. So if we just open up Validate, we will get this sort of menu where we can create a new session. So I'm just going to create a new session. And we can use a volume or an arbitrary line for this session. So I'm just going to use a volume. So we can use any of the volumes we have in our project. And that will open up Validate, which is this interface here. Again, is one of those expression windows where we can test different parameters before we actually generate any results. And immediately you can see we've got here 3 different types of model. So we can create the layer model, which, as I mentioned, has been available for a few months. And then we've got the wedge model, which we can create either with wells down here or without wells. So if we just create one using wells, so well markers, then we get immediately a box here, which is our wedge. But what we can do now is go to a slice that intersects our well. So we could either select an inline or a crossline manually and type here some type of number, and it will go there. Or we've got this new drop-down menu, which allows us to go directly into a line that intersects a particular well. So now if I go to this line here, that line intersects Xdale 1. And you can see immediately the well appears here, and we've got the markers as well. So now we can set the shape of our wedge. So we can either manually move the extents of our box by just moving these handles, or we can type here what sort of inline crossline time we want for each of these locations. Another option is to use markers. So we can use a marker for our top of the wedge and another marker for the base of the wedge. So that's exactly what I'm going to do. So I'm going to take my top reservoir as my top marker for the wedge and my base reservoir as my base marker for the wedge. So now you can see the wedge just covers the area here, the interval between my top and my base reservoir. We can change a number of different things. We can change the overburden as well manually. We can change the number of traces before and after the wedge. I think with this, we have a good wedge to start with. So now we can hit proceed. And then you will see that the screen now zooms into that box. And we can see how our wedge compares with our real data. So this is the model we get here. So just 3 simple layers. And now we have to populate this model with different rock properties. So to do that, we've got different options. So we could go either into this Manage Rock Properties tool, and this will allow us to basically define manually some rock properties. So we could enter a new rock with a certain velocity, a certain density that we know. We could use rocks from well logs. So that means we could create a new well log set. So basically, I'm going to say I want to create a well log set for Xdale 1. And I select my well here. I select my BP log, my BS log, and my density log. And then I could add new rocks based on this well log set. So if I do this, then it will essentially allow me to create rocks that later on I can use in a different slice to the one where the well is sitting. There is also a fluid substitution available there in case you want to run fluid substitution. But another way we've got is if we already have a well log set, like the one I defined, we can just use the well log set. And in here, we can select use the wells that intersect the slice. So if I do that, then this means it's going to take the well log set I defined for this well, and it's going to propagate the properties isoproportionally for the different layers. So it's going to take my BP, BS, and density for each of the 3 intervals I have defined here, and it's going to propagate them isoproportionally into my model. So if now we go into the forward model, we will get a synthetic. There we go. So now we can compare our synthetic with our input data. And the first thing you will notice is that the polarity looks reversed. So this is because we are looking at an Australian data set. And in Australia, the polarity tends to be the opposite, inverse polarity. So what we can do is rotate the wavelet that we are using, 180 degrees phase rotation, and then the polarity should match a lot better. We can also adjust the frequency of the wavelet that we are using. So in this case, I think it's a bit of a lower frequency. So something like this is giving us a better match. There is also the ability of getting some numbers. So how well does my model correlate? So what I can do is draw a small box here along my well, something like this. And then this will give me a correlation value. So you see there, the correlation around my well location is about 87%. So it's a fairly good correlation. So now we've got our synthetic. I'm using a synthetic Ricker wavelet. We found this is giving us the best results here in this area. But we could also import a wavelet. If you have a wavelet coming from Petrel or ASCII file, you can do that. Or we can also extract a wavelet. We've got a little extraction tool to extract the wavelet from the Seismic. So now if we are fairly happy with our synthetic, we can apply variable density. We can apply some color blends into it. So what we can do is go into our blend properties and display a color blend. So now this is going to apply frequency decomposition and color blending to our wedge. So now we probably have in our project an existing color blend. So if I go here, I have available a number of different things, so a number of different things I can look at, and also all the volumes that have the same extents and the color blends that have the same extents in my project. So now if I select a color blend that I have already in my project, so this one is created on real data, I can start to compare my real data with my synthetic data. So the first thing to do is to match the frequencies that we are using. So on our real data here, as you can see in the name, we are using constant Q methods, which is already set for our synthetic, and we are using 183557 Hz. So if I use the same frequencies in my synthetic data as I have in my real data, so I'm just adjusting that. Now we should have something that we could actually compare because we are looking at the same frequencies. We will also need to adjust the scale. So I'm going to select here the same color blends as I have in my real data to use the same scaling for our synthetic. And we will have to adjust also the pose scale. So now we should get a wedge that is using the same frequencies, the same methods, same scaling, and the same pose scale as our input data, as our real data. So we can start to compare them. So we see that at our well location here, we've got some kind of green to blue response. So that is a thickness of 51 milliseconds, which is what we found in the well. So obviously at the well location, the wedge should match fairly okay. We can see it does. So it has this sort of bluish response. And then as we move away from the wedge and as we go into thinner areas, then we start to see different colors. So we start to go into pink, red, yellow, white, eventually some kind of light blue. And if we go to our real data, we see those colors in many different places. So for instance, here we get a lot of pink, there we get a bit of yellow, then we get white, then that light blue. So it's kind of suggesting those thickness variations that we see in the wedge. So it's fairly easy to see a color in our real data, like this pink, and say, okay, what thickness that color actually corresponds to in my wedge. So for instance, in this case, 32 milliseconds. So just by using this approach, we can get immediately some thickness estimations. And if I just go back a bit to the slides, now we can see, as I was mentioning, just to recap a little bit, different colors in our real data will correspond to different thicknesses in our wedge, and we can start to look at them and essentially make those thickness predictions. So you can see how different colors will have different thickness values in our wedge. So now taking this a little bit farther and looking at a time slice, at the time, a horizon slice as we were looking at before. So here we've got the Esdale-1 well, which, as I mentioned, it had this bluish, greenish response, which matches with our model. So that thickness there at our well location was 51 milliseconds, which, using the velocity that was measured in the well, correspond to 75 meters of sand. So now if we know that particular thickness, can we predict and estimate what sort of thicknesses we will have in different places of the channel? And I think the answer is, yeah, probably we can. So if we look at Esdale-2 here, where the well is drilled on this sort of pink, but very much on the edge of the pink response, very close to the yellow response. So I would say that is somewhere around here. So then if we go into our wedge, we can see that is around 27, 28 milliseconds thickness. If we use the same velocity as we have measured in our Esdale-1 well, then that corresponds to about 40 meters of sand, and the well actually encountered 37 meters, so it was not too far off. So just to summarize, by creating these wedge models, we have been able to get a better understanding of our color blend responses and get some thickness estimations. So I think that's it for today. Thank you very much for your attention. And if you have any questions, you can just type them